We just spent a few minutes with the NDP router address acquisition process with the router solicitation and router advertisement. And I'm sure you'll agree with me, straightforward process, very straightforward. You'll see the same here with the NS and the NA, but there's an address in here I need to introduce you to, and there's a little bit of calculation involved. And it's also going to explain something else we've been seeing on the router with IPv6 that we haven't talked yet about. So let's just dive right in here. We've got our neighbor solicitation and neighbor advertisement messages, and they really replace ARP in IPv6. There is no address resolution protocol in IPv6. The NS serves as the rough equivalent to the ARP request in version 4. And the main difference is that the ARP request asks for the MAC address of the device at a particular IP address, say 172.111. We know that the neighbor solicitation message is similar, but the destination address is a little different. I'm going to be honest with you, as I always am. The first time you see it, it's going to be a little odd. And it's destined for what we call the solicited node multicast address, the SNMA, of the host whose MAC address is being requested. What the heck is a solicited node, you ask? Well, don't feel badly if that was your question, or even if you had a little mild profanity in there, because that was pretty much my reaction the first time I saw it. Now, the one thing I want to mention up front before we get into the calculation is that the SNMA is used for other purposes besides NDP. A lot of other purposes in IPv6 that you'll run into later. So you just got to go on faith right now that this makes sense, because it's going to seem a little odd. A multicast destined for the solicited node multicast address, it's actually kind of a built-in range, because it's going to go to some hosts on the local link, but not all of them, just the ones that have the same last 6 hex values as the IPv6 address of the host whose MAC address is being requested. And when you look at that, you think, well, what are the odds that multiple hosts on the same link are going to have the same last 6 hex values as the version 6 address of the host whose MAC address was just requested? Well, the more hosts you have, the bigger the chance. I admit to you, with just a couple of hosts, the chances are pretty low. But we also want to know how to calculate the SNMA, where it came from, and also where to find them on the router. Because we've not just seen one SNMA to this point, we've actually seen 2 of them. And if we go back to show IP interface, I bet you can guess which 2 addresses here are actually SNMAs. And that's these 2 addresses, these 2 joined group addresses that we have yet to discuss. And we didn't join any of these groups, of course, manually, but we know now that FF02:1, that's all IPv6 hosts, FF02:2, all IPv6 routers, and then these 2 longer addresses down here are the SNMAs. Also, the end of one of those might look a little familiar if you look elsewhere. We've got a 990 up here at the end of our link local address. I don't know if that's a coincidence or not. We're going to find out here very, very shortly as we talk about how to calculate the SNMA. And by the way, the reason that we saw 2 SNMAs there is that one is for the global unicast address and the other is for the link local address. Now, how did the router come up with these SNMAs to begin with? Well, here's the deal. The SNMA always begins with FF02:1 FF. Now, I put the uncompressed format up there for you, but you don't even need to do that. If you just take the last 6 values of either the global unicast address or the link local address and tack them on to the end of FF02:1 FF, you're done. That's it. That's all there is to the SNMA. The only thing you got to watch here, Bulldogs, is this. You can't just take the last 6 hex characters of the compressed version of the global unicast address or the link local address. You have to uncompress them and get the last 6 characters. So let's do a little practice here. What are the last 6 hex characters of our global routing address when it is uncompressed? Pause the video, get a little practice in. Maybe you can eyeball this one and tell. Just be careful. And let's take a look at that. Going from left to right, we see some leading zeros there in the 4th block that we put back in. And then we had our double colon there for our 0 compression. And since we had 5 blocks here, we need to go up to 8, so we put 3 blocks of zeros in. And then for that final block, we put the leading zeros back in 000, and this is the uncompressed address. These are the 6 characters you need to add to the end of the SNMA prefix. And then frankly, you're done. So if you just put 00:0001 on the end of that prefix, you get FF02:1, FF00:1. And that's leading zero compression, of course, applied to the last block. And you want to go ahead and do that because you know when you check your work on the router, then the router has already done the compression. Does this match one of the 2 group addresses that we have up here? It sure does. FF02, I'll even slide it over for a comparison there. FF02:1, FF00:1. So the theory holds up perfectly, and we know that that is the SNMA for our global unicast address. So this one, and you would suspect just by looking at it, it ends with 990. This must be the one for the link local address. But how did we get there? How did the router calculate that? Let's go ahead and walk through this one. What are the last 6 hex characters of our link local address? And you can pretty much do that one just by looking at it. I don't think you'd have to write that one out, but doing the uncompression practice is a good deal. So let's have a look at it uncompressed. At the beginning of the address, which we're not terribly worried about right now, but if we're uncompressing it, let's uncompress it. We know we see 5 blocks overall in the compressed address, so we know that zero compression is representing 3 blocks of zeros, so we put those in. The block with 21B, we put 1 leading 0 back in. The 6th block is fine. The 7th block is fine. And in the 8th block, we needed to put 1 leading 0 back in, and that's a pretty important leading 0. So the last 6 hex characters here are C20990. So you tack that on to the end of the SNMA group, and that's what you get. FF02:1, FFC2:990 with leading 0 compression, of course, applied to the final block. Does that match the last remaining group on the router? Man, I hope so. Let's take a look. And it does. Already highlighted. So we've got that one right there, FF02:1, FFC2:990. The theory is right on, and we'll take that. So there's something we need to finish, though. We never really did finish the neighbor solicitation, neighbor advertisement swap here. So the neighbor advertisement, that is going to be sent in reply to the NS, and it's going to be a unicast. It's sent directly to the host that originated the neighbor solicitation. So what happens here is that one host will answer the other host's neighbor solicitation with a neighbor advertisement. And remember, of course, with ARP, the ARP cache, well, we have the same situation here. We have the neighbor discovery protocol neighbor table, and host A is going to pop that address in there to its neighbor table, the NDP neighbor table, and frankly, we're done. So the actual exchange of messages is very simple. What took most of our time here and what we want to have down cold for the exam is the process of calculating the full SNMA. So that is it for our discovery. Now in the next video, we're going to take a look at DHCP, because DHCP is so important to version 6. We actually have 2 kinds, and we know if there's 2 kinds of anything, we got to have the differences down pat for the exam, and we certainly will. And that is all coming up next.